Hello everyone, these are the 8 algebraic identities that we are going to prove today. The first one, which is a plus b whole square equal to a square plus twice ab plus b square, we are not going to prove it directly. We shall prove the second one first and then prove the first one. And let's begin. Here we have a minus b whole square, and by the definition of square we know that we need to multiply the number 2 times. So that is what we are doing. We are writing a minus b 2 times, and then we need to multiply the first term with both the term, right? And when we multiply a with a, we get a square, and when we multiply a with b, we get ab. But the negative sign comes here because a is positive and b is negative. After we are done with a multiplied with a minus b, we need to multiply this minus b with a and minus b with minus b. So minus b with a gives us minus ba, and minus b with b minus b gives us plus b square. And you probably remember that two negatives make a positive, and the opposite signs gives us a negative sign. And then this ba here can be written as ab, because we know that multiplication is commutative, that is a into b is equal to b into a, and 2ab out here gives us twice ab. Because both of them are negative, hence we need to add the terms, and we get the formula for a minus b whole square as a square minus twice ab plus b square. For the a plus b whole square formula, this is quite easy. You just need to make all of them positive. That is the proof. The multiplication and the techniques are all same. Just make all the negative numbers positive and you have the proof for a plus b whole square. And that is the reason I did a minus b whole square at the first place. Now what if instead of a plus b whole square it was whole cube? So removing this 2, if it was 3, then we would have to multiply another a plus b. But we know that a plus b into a plus b we just did, which is equal to a square plus twice ab plus b square. Hence we remove this much part and we write a square plus twice ab plus b square instead of a plus b into a plus b, and then we multiply this entire thing with this a plus b that we have added, we have multiplied extra. Hence we take this a square plus twice ab plus b square and place it out here, and then multiply the third a plus b. So we need to multiply the first term with all of them, each of them, right? And then we need to multiply this second term with each of them. So what result shall we get from this? We have a into a square, that would be a cube, then twice ab into a would give us twice a square b, a into b square would give us a b square. So the multiplication of a is completed. Now the multiplication with b is left. Hence we have, since all are positive, it's quite easy. So this would be a square b, then b into twice ab would be equal to twice a b square, and b into b square is equal to b cube. So the multiplication of b with a square, b with twice ab and b with b square is also done. All we need to do now is arrange these 6 terms into the formula that we already got. How do we get it? You can see that you have twice a square b and you have another a square b here. That is, in total this 2 gives us 3a square b, and also this twice ab square and this ab square together gives us 3ab square. Hence we can write the formula as a cube plus thrice a square b plus thrice ab square plus b cube. And if you take 3ab common out of the two terms, these two terms, if you take 3ab common, you can see that there is a factor 3 and there is a factor a common to both and also b common to both. Hence 3ab, if you take common, we need to multiply what to 3ab to make 3a square b? We need to multiply a, and we need to multiply plus b to 3ab to make it 3ab square. So that is done, and we have the two results for the formula. One is a cube plus thrice a square b plus thrice ab square plus b cube, and the other one is a cube plus thrice ab into a plus b plus b cube. So these are the two formulas that we have already written, and you can see that in number 6. Here you have a cube plus thrice ab into a plus b plus b cube, and here you have a cube plus thrice a square b plus thrice ab square plus b cube, right? And till now we have proven this number 6, number 1 and also number 2. Now we shall prove number 7 from 6 itself. So in a plus b whole cube formula, I am going to remove all the plus sign and make them negative. So, and let us just adjust the signs now. Now a minus b whole cube is nothing but a minus b written 3 times, and 2 of them together makes up the second formula of a minus b whole square. And we know that the formula for a minus b whole square is a square minus twice ab plus b square. Hence we make it plus, and again we have a minus b out here. So now this a have to be multiplied to all these 3 terms. So a multiplying with a square will give us a cube, and a multiplying to minus 2ab will give us minus 2a square b, and a multiplying to b square will give us plus ab square, because here a is also positive and b square is also positive. So here we need to make this plus sign, and similarly for minus b also, if you check it, we will have minus a square b, then plus twice ab square and minus b cube. And in this result you can see that ab square is positive, ab square is positive here and ab square is positive here. Hence it is plus thrice ab square and minus thrice a square b. So the formula will be reduced into these two forms, but it's easier to remember where the minus sign falls by looking at b, because b is negative. Hence wherever you see that b is, there are odd number of b's here and here. You can see here you have 1b and here you have 3 b's. So wherever you have odd number of b's, you put a negative sign before it. Here also you can see you have a thrice ab, so odd number of b you put a negative sign, and here also odd number of b you put a negative sign, odd number of b's you put a negative sign. So wherever you have an odd number of b's, you put the negative sign. So your formula or the proof of this theorem is reduced to this much. You can pause it and note it down. Well, here it was positive. Yep, that's it. Let us do the third proof now. In the third proof, we have a plus b into a minus b, right? So only two binomials, hence let us write it like this: a plus b into a minus b, and we don't have this part. So what is it equal to? We need to multiply, right? So a have to be multiplied to both of them. So a into a gives us a square, a into minus b gives us minus ab. Then b should be multiplied to both of them. So b into a gives us plus ba, and b into minus b gives us minus b square. So again, as we have already discussed, AB and BA are same, hence this BA and AB can be cancelled out and we are left with a square minus b square, and that's our proof for a plus b into a minus b equal to a square minus b square. Now this is the expanded form and this is your factor form. Wherever you see the terms are getting multiplied, right, here a plus b is getting multiplied to a plus b, so that is our factor form. So if you are being asked to factorize a square minus b square, then this will be your factor form. Okay, so we are done with number 3 also, but notice here in all the identities from 1 to 7 except 8, okay, in the left hand side all of them are in the factor form, and in the right hand side they are in the expanded form, okay, or simplified form, what you can say. So here a plus b is the factor, here a minus b is the factor, here a plus b and a minus b, and in this one x plus a and x plus b, here a plus b plus c, so on, right? And on the right hand side of question number 8, you can see that a plus b and a square plus b square plus c square minus ab minus bc plus ca is the factor form. Here this is another factor, okay, a plus b plus c is a factor, half is a factor, and a minus b whole square plus b minus c whole square plus c minus a whole square is another factor. Anyway, we are done with 5 of the proofs, we are left with 3 of them. Number 4 is very easy, so let us do number 4 first. We need to find the value for x plus a into x plus b. So like previous cases, multiply the first term with all the terms in the other binomial. So x into x is x square and x into b is bx, and then a into x and a into b, which is equal to ax and ab. So in these two terms you can see that you have x common, and hence you can write x square plus b plus a, right, and then x plus ab. And you know that addition is commutative, hence you can write x square plus a plus b into x, b plus a can be written a plus b, 2 plus 3, 3 plus 2, all are same, plus ab. Now that's your formula for x plus a into x plus b. Now this formula is actually the formula for the middle term factorization of quadratic equations. Quadratic equations middle term factorization you have already done, and this formula is for that only. Here you can see that the middle term a plus b into x is being splitted into 2. right, in such a way that the coefficients on multiplication is equal to the constant. Okay, now let's move on to the next proof. So 4 is done. Next proof is a plus b plus c whole square equal to a square plus b square plus c square plus twice ab plus twice bc plus twice ca. And from this line to the other line, it's quite easy. You just take 2 common from these 3 terms and you get this result, right? So we are going to prove up to this line only. Last line is almost obvious. As you know what square means, that is equal to a plus b plus c into a plus b plus c, right? We need to multiply it 2 times because it is square. So by the same rule as binomials, you need to take the first term and multiply with all the 3 terms on the other trinomials. Here trinomials are being multiplied, so we will not describe it every time. Now we shall do it directly. A into a square, a into b, ab, a into c, ac, but I will write ca. I always follow the symmetrical order, and you also follow, things will become more easier. That means a, then b, then c. From a to b, then b to c, then c to a. Write it that way. All formulas will become easier to remember. And then we have to multiply b with all the 3, right? This 3 we need to multiply. So we shall have b square plus, sorry, not b square, b into a first, right? So that is b a, but we will write ab. Then b into b is b square, then b into c is bc, and then c have to be multiplied with all the 3. So ca plus cb, instead of cb we are writing bc, cyclic order, and then c square. And you can notice here that you have one AB and you have another AB. You have one CA, you have another CA, and you have one BC, you have another BC. So 2 AB, 2 BC, and 2 CA, and 1 A square, B square, and C square. Hence A square plus B square plus C square plus twice AB twice BC plus twice CA. Now all are positive here. Instead of that, if I make this C negative, what will happen? Now as I told you in the previous, while doing that cube proof, that wherever you find odd number of B, I told you to give it negative, because there we had only A and B, right? But here we have A, B and C. So wherever you have that negative term, so the negative term here is C. So wherever you have odd number of C's, you need to give the negative sign, and that will be your proof. So here you have one C, so I give a negative. Here we have another C, so I give negative. Only one C, one is odd, right? And then here we have this CA, instead we can write minus here. Then we have BC out there, this place, so we need to write a minus here also. Then do we have any other BC? Yes, we have. On this place we need to give another negative sign, and here you have C, but it is not odd number of times, it is 2 times. 2 is even, hence it will be positive only. So your proof for A plus B minus C whole square becomes like this, but we need to change our last line where this BC and CA will become negative. Oh, here also the CA should be negative, so negative and negative, right? So that is your proof, and you can note it down for a plus b minus c whole square. But let me tell you the tip how to just write the formula directly and remember for each of the negative terms. Just now I gave you a shortcut tip actually. You just see how the formula can be written. If you remember the first formula of a plus b plus c whole square, a plus b plus c whole square is a square plus b square plus c square plus twice ab plus twice bc plus twice ca. Now if c is negative, one term is negative, then wherever in twice ab part, this 3 will be always positive. Okay, whatever it is, negative or positive, doesn't matter, this 3 will be always positive. Only changes should be made in twice ab, twice bc and twice ca part. So if only one negative sign is there, like this minus c, wherever you see c, just put the negative sign. So in these two places you see c, so you put a negative sign out there. If you have two negative signs instead of one, then what you do, you have two negative signs now, you need to change the signs, right? How do you change the sign now? I have given all of them negative. Is it possible? No. So wherever you see this BC together, you put positive, others will be negative. So do you notice the difference? Whenever you have two negative terms, you need to put only one positive wherever both the negative terms occur. Here both the negative terms occur, we have given a positive out here, and the other twice AB and twice CA factor we have given negative. But when there was only one negative sign, for example if this one, then what you need to do, you need to put the negative sign wherever this odd number, this negative number appears. So it appears on BC, so negative, it appears on CA, they are also negative, but it doesn't appear on twice AB, hence it should be positive. And with practice you might not even need to look after these things. While writing only, you can keep on writing the formula with its sign itself, because you see here two positive AB, so we write positive sign. We see a positive and a negative in BC, so we put a negative sign, and on C and A you see a negative and a positive number, hence we put a negative sign out here. Anyway, 7 of the 8 proofs are already being done. We are left with the last one. Number 5 is also finished, only number 8 is left. In 8 we shall do it from the right hand side, and that will be easier for us. We will do it from the right hand side. In right hand side all we need to do is just multiply it, and let's see how we do it. So the right hand side we have a plus b plus c into a square plus b square plus c square minus ab minus bc minus ca. You can see here they are symmetrical, a then b then b then c then c then again a. This is not symmetrical, the cyclical order that I told you. And now we shall need to multiply a with all the 6 terms here. So in the first line I am going to write a into a square a cube, a into b square a b square, a into c square a c square, a into minus ab, that is minus a square b, then minus a b c, and then a into ca minus ca is equal to ca square. Then for b I am writing on the second line here b into a square, so that is b a square, but as I told you the cyclic order I will write a square b, that will be easier. A square b, then b into b square, that is b cube, b into c square, b c square, b into minus ab, so that is minus a b square, b into minus bc, that is equal to b square c minus b square c, and b into ca is equal to minus a b c. You could have written bca, but I have written abc at one place because I have maintained the cyclic order, because multiplication is commutative. And if you don't do it, try to write that line yourself in your copy without arranging it in the cyclic order, and you will see the problem in the next step. After we complete this multiplication, whatever we are going to do, the cancellation, there you are going to face the problem, and do try it. If you don't face the problem, you will not understand. Anyways, c into a square is ca square, then this would be c into b square, so b square c, c into c square, c cube, then abc, c into ab, then b into c square, this would be bc square, c into bc, right, and c into minus ca, so that is minus c square a. Now I need to do the cancellation. I have a b square positive out here, and I also have a negative a b square. Where is it? Here. Then we have a c square, positive ac square. So where is the negative ac square? Here, and I had to search it because I did not maintain the cyclic order in this place. I wrote ac square, I should have written c square a, then that would be easier for me to find. Then I have a square b minus, so this is plus a square b. Then I have minus c a square, so I will also have a plus c a square. So gone. Do I have anything more? Yes, I have plus bc square, and then minus bc square. Then here I have not this one, the below one, this one, bc square, and then we have another one, this minus b square c and plus b square c. So almost all of them are gone. We are left with only a cube, b cube, c cube, and we are also left with minus abc here, minus abc here, and minus abc here. So 3 abc. So our final result is a cube plus b cube plus c cube, and abc's are negative 3 abc's, so that is equal to our left hand side. So we started with our right hand side, right, and we reached the left hand side. So that's our proof. Okay, now we need to also prove the next part, that is this part. The first part is already done, right? This part is already completed. We need to do the second part, that half into a plus b plus c into a minus b whole square plus b minus c whole square plus c minus a whole square. And for that we write the formula and we multiply half and 2 to the terms a plus b plus c. Since we multiplied a half, we need to multiply a 2. Instead of multiplying it here, I am multiplying it on the other place, because multiplication is commutative, right? So we have it this way, Now if we take this 2 and multiply to each one of them, we shall have half into a plus b plus c, same as it is above here and here, and this 2 will give us twice a square, twice b square, twice c square, then twice ab, twice bc, and twice ca. So here we have 2a square, 2b square, 2c square, and this twice ab, twice bc, twice ca, you know that it twice ab comes in the part of a minus b whole square formula. So b twice bc would come in the part of b minus c whole square formula. Similarly for c, twice ca would come in the part of c minus a whole square formula. And because of this 2a square, we can distribute the a square. 1a square we can give it for twice ab, and 1a square we can give it for twice ca. 1b square we can give for twice ab, and 1b square for twice bc. Similarly for c square also we can do it. And on rearranging this a squares and b squares and twice ab, we can write it as half into a plus b plus c, which remains same as above, and then we have a square minus twice ab plus b square. You can see here we have one a square here and the other plus a square here, so it is matching with twice a square. This b square and b square, 2b square matched. C square and c square equivalent to 2c square here. So twice ab, twice bc, and twice ca are ultimately equal to the previous step. Hence, these parts inside the bracket are nothing but the formula for a minus b whole square. So this is a minus b whole square, this is b minus c whole square, and this is c minus a whole square, and hence that's our proof. And we can write half of a plus b plus c, and then those brackets, and a minus b whole square plus b minus c whole square and c minus a whole square. That's the proof for all the identities. In the next class we are going to do the application for all the identities, and you are going to get your next class tomorrow itself. So just half an hour, and I hope you note all the proofs and show it to me in your class copy. You note them down in your copies and show it to me.